Hi, everyone. This is Mike Rago with Silent Signals, joined by my good friend Chet Hosmer, a professor with the University of Arizona. We appreciate you attending our session today titled Uncovering Covert Channels in Your IoT Networks. This presentation is a mashup of a variety of research we've done over the years, including a presentation we did previously for the RSA conference in 2018. In terms of the overall research, we've looked at a lot of challenges across IoT, industrial IoT, ICS, and OT networks and devices. And if we take note of current day challenges, threats, and even breaches that have occurred, the systemic thread that we see across all of this is that there's really poor visibility and a flawed supply chain. And what we mean by that is if we take note of, say, for example, Oldsmar. So recently there was a hack at a Florida city water supply company. And this involved the fact that in this OT environment were a lack of security controls that allowed, through TeamViewer, a breach of a Windows 7 laptop, which then allowed access potentially to the water supply environment. In looking at this, some of the challenges that we see are that, across OT environments and even ICS environments, when we talk about, for example, municipalities, we find that a lot of these environments are underfunded, lack of security controls, and really just a lack of money overall to really, provide the security in place to really identify a lot of these risks and threats when they occur. Fortunately, in this case, it just so happened someone was at the facility and started to see the imminent threat by the mouse moving around on the actual computer as the threat was starting to occur. But in general, that was pure luck. And what we've seen with SolarWinds, Sunburst, and many of these others is the fact that a lot of these breaches can be quite rampant. So when we look more broadly at SolarWinds, we see the thousands of organizations that have been impacted by this. There's not only the threat of a supply chain, which allowed a Trojan to be deployed across many of these environments. But when you think of the aftermath of that, and whether that be remote command and control, when you think about exfiltration of data and many of these other things, there are a lot of covert channels that are going on across many of these breaches that most organizations are blind to. And these two examples are prime examples of that. So, what we have found doing a lot of research over the last number of years across IoT, industrial IoT, ICS, and OT in general is that there is a supply chain challenge and problem. There's so many different operating systems, communication protocols, wireless and wired. And as a result, it's really kind of the Wild West. And although that standards exist out there, they're not frequently adopted. And furthermore, the environment in terms of those standards is also very fragmented as many standards kind of conflict with one another. When we take a deeper look at a lot of these threats, it's certainly far different than it was 20 or 30 years ago. And now with a plethora of operating systems, let's say, for example, Nucleus. Nucleus is this foreign operating system that a lot of people just don't really know much about or have even heard of before. When we work with organizations and identify risks going on in their environment, or we're doing investigations, these types of operating systems, well, although Nucleus exists on over 1 billion devices around the world, it can be found in anything from a smartwatch to an industrial control system type device. Nucleus itself, in our research, we discovered that there were a lot of covert channels going on. So research that we did a number of years back on just a simple smartwatch determined that that smartwatch communicating to an app on a mobile device allowed covert channels back to China. And as a result, we disclosed that research. In addition, when we look at many of the other protocols in the environment, whether it be wireless or wired, we now have progressed beyond just Bluetooth and Wi-Fi. And now we've got Z-Wave, Sigfox, LoRa, and many other protocols out there too. And so it becomes more and more challenging for organizations to determine, how do I protect all of this? Did I even know that some of these operating systems or communication protocols even existed in my environment? We've never even used them. And upon assessments, we frequently come across many of these. It does require a fundamental step back. And when we take a look at NIST's, fundamental CIA, confidentiality, integrity, and availability, if we break these down and incorporate our learnings across all of these different IoT and OT and ICS environments, is that beyond how we look at how we protect data at rest or data in motion, we're now taking a deeper look as an industry at what's actually in use, or furthermore, what is the relationship between all of these devices? We've progressed obviously quite a bit from the traditional client server approaches of many years back, and now with the inflection point, including the cloud and mobile devices and apps and hubs that run many of these IoT or industrial IoT devices, managing and securing all of this has becoming increasingly complex. So when we take a look at confidentiality, for example, many times we find somewhere in that communication chain, things may not necessarily be encrypted and are being communicated clear text. Even the data at rest on the majority of the devices that we've reverse engineered and done testing on include no form of encryption or key management altogether. And that kind of transcends over into integrity too, in the form of thinking about when these devices communicate, what type of hashing and validation and integrity checking is actually being performed between these devices, whether it's machine to machine, whether it's being communicated to the cloud, whether it's being communicated to a hub or some other form of network. And then thirdly, availability. And most importantly, security updates. So availability can certainly include aspects of health checks, redundancy, but one of the key things that we found in a lot of the research we've done and a lot of the devices and networks and hubs that we've reverse engineered is that there is a big lack of security updates. Either they're not really provided by the vendor that sold the device, or furthermore, lack of automation to update that within the device itself, either automatically or programmatically if the user wants to go into the web interface or something else and perform those updates. So a lot of these devices sit out there forever, never being patched. So we've done a lot of research across wired and wireless communications. And furthermore, when we think about some of the protocols we're going to talk about next, there's a lot of protocols from way back that still exist in today's environments. They may range from new implementations of Modbus to things like RTSP and many of the other protocols out there. And then, of course, today with the explosion of IoT devices and new forms of wireless communications across Zigbee, Z-Wave, LoRa, and others, there's a lot that each and every organization needs to consider in terms of how they look at this and all the different methods for these covert communications. So one really good example is some protocols that we kind of peeled back and took a closer look at. One of those is Simple Service Discovery Protocol, or SSDP. And this UPnP type of communication allows devices within IoT to communicate with one another. And there are different subsets of different commands and different communications that are performed. Some of the things that we took a closer look at are things like mSearch or Notify. In the case of mSearch, where you put a device on a network, it's going to send out automatically discovery packets on the network to try to discover other devices that it may want to communicate with. And the same thing with Notify, where it not only announces itself on the network and on a regular basis, but also when it's removed from the network too. And we'll talk more about that in a moment, but we did a lot of analysis around this and sort of the lack of integrity and even confidentiality around some of these protocol implementations. Also with RTSP, or real-time streaming protocol, RTSP has been around for many, many years. So when you think about the physical security in your environment, in your building, in your data center, or other places, these old school video cameras still exist today and are still being purchased and deployed for that matter. But this old school protocol is used in conjunction with video streams and has a plethora of vulnerabilities and risks associated with it that we'll show examples of in just a moment. And then the other thing that we've really uncovered are those aspects around cloud providers. So many of these devices, as we know, communicate to the cloud, but how they communicate to the cloud is a byproduct of the implementation. Is it the device that is directly communicating with the cloud? Is it the hub that's managing that device that's communicating to the cloud? Is it the app that you're using to manage that device that's communicating to the cloud? These are all additional layers that need to be considered when looking at many of the risks and vulnerabilities that can occur from having these devices in the environment. And what we're going to show next is the exposure around UIDs, MAC addresses, and even passwords that have been exposed as a result of this. The first example here that we'll use is kind of an old school video camera. And with these surveillance cameras, we mentioned RTSP, real-time streaming protocol. And again, although this is an old school protocol, it still exists in many environments today. But what's interesting about it is these devices are not normally managed by IT. They're normally managed by the physical security team. And, while although those folks are probably very good at how they handle physical security, do they really understand the network protocols behind them that may be exposing some of this data? This is just one example of that. So in this particular environment, we ran analysis around that. First and foremost, we found that all the communications by default were clear text. And in addition, as we look deeper at a lot of these different devices, we found that to be the norm. And while although some of them provided the ability to enable SSL, fundamentally it was turned off by default. And so just the communications back and forth on the local network were all clear text, but they also typically communicate with some kind of data storage device. And for that, now in today's world, typically provide a web interface where people can go in and view the video feeds or show them, of course, on a screen in the physical security room so people can monitor those video feeds. But what we found is that many times those web interfaces also have no authentication. What we found very alarming, and this very much in the context of this presentation, is that there's a huge lack of not only confidentiality, as we've mentioned, but also integrity. And because of that, a lot of data can be inserted within these communications, within these protocols, and within the payload to communicate nefarious things. For example, we've tested and demonstrated in the past where you can basically expose these by leveraging those payloads and those communications to insert data into those fields that could be used for implementing CNC, infecting the device, and furthermore for exfiltration. This is another example, but more in line with what we mentioned earlier around SSDP. So in this particular example, this is an actual spy camera. Spy cameras, as we know, are available in a variety of different forms. They may be in the form of a USB thumb drive with a hidden camera, or a smoke detector, or a clock, and many, many other forms. Of course, it's meant to be, invisible, to the naked eye, right? Such that even though it's clear and present in the environment, you don't know there's a video camera built into it. What we found as we implemented these is that many times they can be configured to communicate over your wireless network or to an app on your mobile device, either over Bluetooth or sometimes Wi-Fi. But it's as we started to peel back the protocol and these communications that we found a lot of alarming things. First and foremost, this spy camera wasn't quite as covert as you might think. It may be to the individual that person may be spying on, but in terms of the person performing the spy activity, that data may end up elsewhere. So we actually discovered that as these were communicating back and forth and communicating over the network, whether it be via an app or directly over the Wi-Fi, that it was transmitting things like a UID, a MAC address, and even the passwords in clear text. So fortunately, we had a test network and we're using dummy usernames and passwords, but we found this information communicated clear text over the network. But furthermore, what was even more alarming was nowhere in the documentation did it say this information would be stored in the cloud. And as a result, we saw all our video recordings being sent to Alibaba in China and communicated clear text over the internet. And what was even more alarming than that, where they were stored in the cloud was almost like a massive Google Drive of everybody's shared videos. So as we went out there to view our videos, we found many other videos as well. So 1 week after we had disclosed this, coincidentally, the US put a ban on the exact same cameras we had covered in the presentation. Not to say that we influenced that or we had, any kind of play in that, but it certainly was quite a coincidence after we had released the research. And with that, I'll turn it over to Chet.
Great, thanks, Mike. We want to talk a little bit about industrial control systems, and we wanted to pick a particular protocol that we wanted to actually examine and kind of provide a little background on that, and then actually show you how we could intercept that protocol and actually figure out what was actually going on. Because these protocols were originally designed not to run over the internet, over TCP/IP. They were direct connected. So Modbus was originally created by Modicon back in 1979, and it was a serial communication protocol. And then Modicon was acquired by Schneider Electric, a very large industrial control provider, which uses it today. My first involvement was back in the early 90s when I was developing an AI heuristic-based hydroelectric control system during a research project funded by Niagara Mohawk. So my involvement with Modbus and those protocols go way back. If anybody's interested, this was the review article that was peer-reviewed in Hydro Review back in 1992. And I'm exposing how old I am. Anyway, just to talk about the basics of the Modbus protocol and how it works, and one of the reasons why it's so popular, but also one of the reasons why it's so vulnerable, is you have clients or multiple clients that need to make requests to specific units. So they have a server that's in between that you're going to communicate with. So the client basically makes a request to the server, and then the server responds to that request. And that could be to read some information from one of the units, or it could be to make a setting or write some registers or do those kinds of things to the industrial control appliances that are attached and controlled by the server. So you would think I have some protection here because I have a server that's basically translating those requests and properly assigning them to specific units and then responding back to the client. So let's take a look at that packet structure and how this actually works. So the Modbus application header has basically 4 different components: a transaction ID, a protocol ID, a length, and a unit ID. So the unit ID is what unit do I want to communicate with. The transaction ID is because they're going to issue, this client could be issuing multiple transactions to the same server for the same unit or for multiple units. So understand these things are going on quite rapidly. And then there's a function code. Basically, what do I want you to do with this particular request? And then I may have to provide you with some data that's associated with that particular request in order to be able to perform the operation. Maybe I want to specify a specific register. I may want to write some data to a specific value within that area. So nothing wrong with it there. So how does it get the response? Well, when the response comes back, the response packet looks almost identical to the request packet. Basically, there's a transaction ID, a process ID, a length, and a unit. So in order for the client, in order to basically collect this data back from the server, it has to associate, right, the request with the response. And so they do that by matching up the transaction ID and the function ID and the unit ID coming back in the protocol. So understand that this all operates in the payload section of TCP/IP. Right, so it's below that particular level. If there's an error that occurs that's defined by the server, the same function code byte comes back, but the most significant bit is set, indicating there was some error, and then there's an error response that's there that we would want to basically take a look at. So what are some observations then based on this? First of all, the basic Modbus protocol has no built-in security or integrity validation. Thus, any security or integrity must be provided by either TCP or the TCP exchange must be contained in some sort of wrapper, in order to do it. So you have to add security on top of this. And typically, as Mike said in some of the other protocols, it's typically not turned on or not used. And it also makes the process more complicated. And one of the reasons that it's not used is because, hey, all of this is running inside of our internal environment. Why are we concerned? right? So the insider threat and other compromises that can occur inside the organization are not considered. So, but by capturing all the TCP/IP traffic, we could build a script that matches the requests to the responses, translate the function codes to readable messages so we know what they were. We can translate any of the error codes that were there, and we can catch and report any error responses. And we can report any orphaned requests or unsolicited responses, which would be very unusual. In other words, you would expect in TCP/IP that I'm going to get a response to a request. I'm never going to get a response to something I didn't request, right? Those things would be really odd and will probably indicate some sort of compromise. So I'm going to turn this back to Mike. He's going to basically talk about some of the IoT things. Then I'm going to come back and show you a quick demo of how we actually do that capture.
Great, thanks, Chet. So what have we learned through a variety of this testing? First and foremost, why is my username and password being transmitted to the cloud to a foreign country? And by sending out this information, which by the way wasn't even documented, this outbound only data, unless you're filtering outbound, is being sent to the cloud in a foreign country, stored in a drive share that's accessible to everybody. In addition, when considering data at rest and data in motion, there's also the important aspect of data in use in those types of data. For example, we've heard many of the stories around, for example, the use of a mic within many of the IoT devices, including televisions and other types of devices. A good example of that is with a lot of our research in the past around other forms of smartwatches. We had disclosed, for example, not only the lack of resident encryption and data at rest, or lack of data in motion with these smartwatches and how they communicate with an app or communicate that data to the cloud, but furthermore, in looking at how these devices actually leverage other functions of how they interoperate with, for example, an app on a mobile device, is what other types of features are they using on that mobile device that you weren't aware of? Maybe they disclosed it when you installed the app, but fundamentally, there's other aspects that are going on and also being sent to the cloud. The supply chain also for a lot of these operating systems, as we've mentioned, is largely unknown. For example, when we first started research around the Nucleus operating system, we knew nothing about that operating system. And as we started to run tests, do reverse engineering, analyze the network communications, we really started to uncover a lot of those undocumented features. And it kind of begs the question, did they not document it for a reason? Many of the documentation we got were also in foreign languages. And even in the extreme case where you could obtain an update, it would simply provide an IP address with no other information. So definitely suspicious. And as we've demonstrated in this presentation and others we've done in the past, including what we covered in the RSA presentation in 2018, it's quite easy to modify a lot of these operating systems, their software, and how they communicate to embed a plethora of covert data, because there really is no integrity checking whatsoever on a lot of these devices. And also, by adding a device to the network is the ability to weaponize that device, even if it's somewhat passive. So by putting a new IoT device on the network and leveraging a protocol like SSDP with mSearch and Notify and those other communications, other devices are naturally going to respond back. It's sort of an indirect way of footprinting the network without actually running an actual scan of that network. And then lastly, as we've mentioned, other considerations related to this, for example, are the ICS, are the OT, industrial IoT, or IoT devices communicating by means of a hub or a centralized gateway in which they communicate? What's the actual physical security of something like that in a hub? We presented a few years back at RSA how plugging even just a thumb drive into the storage device for all of the video storage, that you could easily, without any access, to log into the device, get a copy of all those videos, store them to the thumb drive, and walk away. So a lot of those things we've implemented over the years on desktops and PCs hasn't really transcended over into IoT yet. So in terms of applying this based on our learnings here, and I'll let Chet kind of elaborate on this as well, is, when thinking about confidentiality and some of the examples we've gone through already is, how is information secured and to what extent on these devices? We find the data at rest and even the data in motion by default is largely turned off. And especially for the data at rest, no resident encryption you can even enable. And furthermore, in terms of the data in use, being able to also hide data within payloads, there's just a huge lack of confidentiality and furthermore, integrity checking, especially to allow these to be used as an avenue for covert communications, for data exfiltration, and also injection and communicating CNC URLs and IP addresses.
Yeah, one of the things we've often talked about is on the integrity side, everybody kind of talks about encryption, right? And thinking encryption is going to solve everything. But integrity is just important of that in this process of being able to make sure that the communications that are happening with integrity. So what type of cryptographic hashing is being used? Some. Are digital signatures being used? Rarely. Are trusted timestamps used? Never. Is blockchain an interesting technology? Was it applied in this area? We've not seen it. In audit, it's rarely captured, but typically never viewed. So even if some of those integrity mechanisms are in place within this environment, nobody's watching.
And when we take a look at availability, we mentioned, the lack of security updates earlier. They're either not available. There's a lot of, vendors out there that just provide no services to manage that, or it may not even be built into the device to go out there and pull down or automatically update the device over time. And now with all the supply chain risks, would you trust it from an untrusted vendor? Which brings up, further questions around, availability as well.
So one of the things that we have built over the last few years is this ability to monitor some of this traffic. And again, we picked one of the ones we've done, which is the Modbus application. So we wanted to actually share that with everybody and actually give it to everybody for free if they want to actually download it and play with it. So this is the analysis of Modbus flow, requests and responses that I mentioned earlier. It's a Python 3 script, so it runs on all platforms. And you can freely download it from the Silent Signals website. So with that, I'll bring up the script. I can get rid of all my screens. And I'm going to actually go ahead and run that script for you. So it's a pretty simple script. It's a script called mpa.py, and you basically specify what directory that you'd like to basically pull some PCAP files from. So I've got a bunch of them in this particular directory. Let me show you a really simple one to start with. We'll look at PCAP3. So what we're going to do is we're doing this by replaying a PCAP file, but you could also do this live, of course, if you wanted to put a monitor on your network. So what happens in this particular case, exactly what I wanted to visualize exactly what we talked about before. We processed 8 packets, and 2 of those packets were Modbus packets, and they were normal. So we had the request going out from at a particular time, and it came back almost instantly. The source IP addresses are the same. 502 is the Modbus port, and then in the request direction, it's targeting the Modbus port, and in the response direction, it's coming back from the port. So we're actually looking at those. So the TID and the PID and the unit ID, all of those match. So what happens if we do something a little bit more interesting and we look at a PCAP file that's a little bit bigger? And this script will run on virtually any size PCAP file that you want to correlate. So we actually look at these requests and response to determine if they're in fact normal. So normal would be, hey, I sent out a request, I got a response, there were no errors, and everything was kosher. So you're basically seeing all of the data that's going back and forth across that protocol here, and you can analyze that. So you're looking at all the normal packets that go back and forth on that particular protocol. But what happens when things go wrong, and what might it mean if they go wrong? So let me scroll down to a couple of the warnings and the criticals that the script jumps out. And this will dump out to a CSV or a JSON file as well if you wanted to bring it into another example. So here's the first warning that we got. So in this particular case, we basically sent out a request by the way, these PCAP files came from DEF CON, and basically, so these were attack scenario PCAP files. I should give them some credit for that. So basically, in this case, we call this a warning because we sent out a request, but we never got a response from the server. So what could that mean? Well, obviously, it could mean that the server's down or not operating correctly or not responding correctly to this particular request. And is anybody watching to make sure that that actually is happening? So we got several of those, which are certainly concerning. And this one that we're looking at came from the same IP address going out to the same destination IP address over the port, and multiple times in a row, it never responded, kind of indicating this is an alert you'd want to know about, that something is not operating correctly within your ICS environment. And again, it may indicate there's been some sort of compromise. But the more concerning ones that we see in many of these is one like this, where we have a missing request. So we have a response that came back from the server that's operating with the unit. The critical device that's controlling those units is sending out a response packet where there was no corresponding request. That implies that the server has been compromised at some level and is trying to send information back to clients within the environment and basically trying to corrupt those. So this is a critical error that we would label in this particular case, because we have multiple cases here where we have a missing request where we got a response back from the server, but no corresponding request. And then basically you can run as many of those as you want. And like I said before, the MPA analyzer is available. It's a Python script. You can run it on any of your platforms, and we can you can get that from the Silent Signals website. So again, these are some of the examples of the requests and response. I gave you the demo. I'm going to turn it back to Mike because we have a few more minutes to kind of wrap up for the day.
Sounds great. Thanks, Chet. So to round things out and really, apply what we've learned today and kind of what we've demonstrated and talked about over the last 30 minutes or so is really, how can you start out next week, and how you could use a tool like this and a lot of the learnings we went through to really perform localized network packet captures in some kind of test location, and use the script to assess your Modbus environment. And furthermore, determine if there are any kind of suspicious or even maybe aberrant behaviors that are occurring. And this can certainly be used to help investigate any kind of suspicious covert communications or hostile type activities. And furthermore, what can be done beyond that. We've also tested this within a Raspberry Pi and other types of environments too. So it's very efficient. You don't need a huge server or even a laptop to run this. And furthermore, if it is an ICS kind of environment, you can even run localized reporting, for example, Grafana, along with an influx database on that device, which would give you some really nice reporting for your operations center if you wanted to operationalize it. Additionally, if you had something like Splunk localized on the network, you could report to that too. We've tested that out with Splunk as well. Or in those other types of environments, if you want to cloudify this and do this in the cloud, we've tested this across Grafana, Splunk, and even have started doing some testing with AWS as well. But as you think more broadly about your environment, multiple locations, multiple networks, is the ability to kind of uncover these anomalous, nefarious type communications, anything that might be suspicious, but also uncovering what might be a hostile location if it truly is or has found a way out to the internet as well, egress as well as ingress in some cases. And this can certainly help with removing the device from the network and helping lock down those communications. And then furthermore, over time, refining those approaches to fully operationalize that. So I'll allow Chet to say thank you as well, but we did want to thank you for your time today. Thank you so much for having us back. We had a great time in 2018 doing the presentation for RSA, and this is sort of our, next version of, kind of an updated version of all the different types of research we've been doing around covert communications, and really appreciate your time today. And I'll turn it over to Chet one last time as well.
Great. Thanks, Mike. Really great to see everybody again. I wish we were there in person, but hopefully we kind of inspired you a little bit to kind of look a little bit deeper into these protocols, use some tools and technologies to actually do that analysis and actually integrate that into your operations. And that's something that we do on a daily basis every single day. And so hopefully that was informative. Hopefully you'll download the scripts that we're providing so you can start to use those yourself and give us some feedback. We'd love to hear from you.